introduce. Hi, everyone. Welcome to the 138th Stanford MedAI Group Exchange session. This week we have Jiangchao from Shanghai Jiao University, and he's joining us to talk about his work on low-rank knowledge decomposition for medical foundation models. He's currently an assistant professor at Cooperative MediaNet Innovation Center at Shanghai Jiao University and a research scientist at Shanghai AI Lab. He received his dual PhD degree in Shanghai Jiao University and University of Technology, Sydney in 2019, and his research is mainly focused on trustworthy machine learning and reasoning. He has been selected as MSRA Star Trek Scholar in 2025. Jiangchao, thank you very much for joining us today. Before we start, do you have any preference on how you would like to take questions? Can we interrupt you in the middle, or do you have designated breaks in your talk for questions?
Okay. Thank you for the introduction. It's very happy to have the chance to share our recent work, LoRKD in MedAI group. Okay. Our slides will consist of 4 parts. We will simply talk about the origin of this work to decompose the medical foundation model, review the related works and our method as well as the experiment. First, following the scaling law about the data and the model size, it's very common that now we have many foundation models in general domain that achieve impressive performance in different language vision tasks. Such success drives us to build a foundation model for medicine to promote the development of medical AI. But before that, I think we should rethink the difference between general vision domain and the medical vision domains. Basically, for the general domain, we can collect a large number of images, easily reaching to the billion scale. And in the object recognition, there are many common patterns that can be shared among the general vision tasks. Besides, we also have high performance equipment to develop, deploy our large-scale model. But for medical domain, it's totally different. The first point is that the medical occlusion device only focuses on a special region of our body. And it's also hard to scale up data due to the privacy policy. Among the tasks, it's hard to find, but not absolute. To find some common object structure between like head CT and the chest CT. Then in this case, if we put these images of different anatomy together for large-scale training, will be not very effective and efficient like that conducted in the general domain. In other words, these tasks are less coupling in common patterns. Furthermore, if we take the computing ability of the medical device into consideration, it's also not high performing. So these are the real-world constraints for our medical domain. Therefore, for medical foundation model, the data heterogeneity, including the modality heterogeneity and the anatomical heterogeneity, is more pronounced for both pre-training and serving. So these important factors that we need to consider for pre-train the medical foundation or use the fundamental for the downstream tasks. Sorry, let me take a headphone. Such heterogeneity usually requires large-scale models to incorporate the discrepancy during training, simultaneously yielding the high cost for deployment. besides, empirically, sometimes the well-trained generalist models even cannot surpass the specialist models in medical domains. So if if you test probe the performance of medical foundation models in the specific task, you will find many times we can train our specialist models that can easily achieve better performance than the medical foundation models. So in here, behind this phenomenon, I think the reason is the data heterogeneity, and our model is not larger enough. So how to address this dilemma? Actually, there are many classical methods in machine learning related to this topic. For example, we can follow the multitask learning paradigm to unify different kinds of tasks in one model to achieve one-for-all training. And or we can just follow the knowledge transfer paradigm, like pre-training, then fine-tuning, or knowledge distillation to transfer or unify the backbone into the downstream scenario. But what we concern what we concern is for multitask learning, and both, as we know, multitask learning includes two main types, like hard parameter sharing and soft parameter sharing. For these two paradigms, the challenging point is that it's not easy to conduct the task balancing during the training. Even we can search for a better trade-off along the parental frontier, like the
I think we lost the speaker again.
Yeah, I can't hear him. Jiangchao, we can't hear you.
Can you?
Yeah.
Oh, yeah, it's okay now.
Yes.
Oh, okay. I'm so sorry. It's because of the internet connection between China and America. I think I now reconnect another internet to so I think the problem is addressed. Okay. Let me continue. Sorry about this issue. So for knowledge distillation, including logic distillation or feature distillation, they mainly target to transfer the knowledge from the teacher model to the student model. But the problem here is what's the relevant knowledge to transfer. Sometimes if we depend much on the teacher models, we may suffer from the negative transfer issue, which degenerates the model performance. So based on the analysis of the related techniques, we try to explore a new method to address the data heterogeneity and at the same time achieve the computing-friendly deployment. Intuitively, what we do here can be illustrated by this figure. Originally, we have unified medical foundation models that can conduct a range of tasks. But directly deploying the medical foundation model can be cost expensive, considering the real-world limitations for each hospital. But if we can decompose the medical foundation models into a collection of expert models in line with the departmental division of the hospital, then maybe we can achieve both specialization and reduce the model size. So that's the intuition of our LoRKD. The question is, how can we design an efficient framework to decompose medical foundation models? Basically, we need to consider how to handle task heterogeneity by the proper decoupling, and how to achieve the computational efficiency, because we may have a range of data for pre-training and distillation, and how to design the balancing strategy among the tasks. If some tasks are pretty easy and some tasks is very difficult. Our idea is motivated by the low-rank adaptation structure, namely LoRa. Following LoRa, we actually can design a very special decomposed model architecture, which consists of a backbone, but with multiple LoRas. We can use this special decomposed model architecture to reallocate the knowledge projected from medical foundation models. And in this case, we can compress the common knowledge into the backbone and use different LoRas to incorporate different task-specific knowledge. And then after training, we can merge different LoRa into backbones to get the task-specific expert models. So this achieved our intuition in the previous slides. So with this idea, we propose our overall framework of LoRKD, which follows the ordinary distillation, but configured with a smaller backbone with a mixture of LoRas as the student model. So this figure figure A here illustrated our design. But for medical image segmentation foundations like MedSam, foundation models may consist of a textual prompt encoder and the image encoder decoder structure. Then our distillation will be performed on the pixel level logics. Well, for the classification foundation models, it only consists of the encoder structure, which is simpler. Then the distillation is performed on the class logics. So for our composed model architecture, we can see that here we just project the foundation models encoder into a decomposed model architecture to incorporate the knowledge, common knowledge into the shared backbone, but task-specific knowledge into the LoRa expert. So one important point here is that the backbone can be very small compared with the medical foundation models. In the following experiments, we will report this phenomenon. The inherent reason is like what we explained in the previous slides. Namely, if the data is more heterogeneous, we will require a larger model to incorporate the discrepancy in learning the pattern. However, if we have proper design in the model architecture to consider this problem, then the model size can be reduced. Another point we should clarify that except the architecture design for the student model, the computation for the mixture of LoRa is a critical point because it's not like the normally low-rank adaptation on the frozen medical foundation models. It's the shared backbone and LoRa will be jointly trained. So in this case, for our mini batch, if different samples correspond to different anatomies, then we need to merge different LoRa into the backbone for different anatomies in our small mini batch. Normally, it will cause our messy code to write. A better way is that we design an efficient knowledge separation convolution. Essentially, they leverage the benefit of group convolution. So the detail is we can stack the input samples into one sample point by concatenating their one dimension. So we can stack the samples together as a one sample point. And then we can also stack the merged model as the groups in each layer. By this way, we transfer the computation like we forward one sample point into our model with the group convolution, so which is computational accelerated in the underlying CUDA operator. So it will achieve fast, efficient training instead you write vanilla messy code to conduct the same thing.
Jiangchao, I think we have a question from the audience. You would like to answer now or at the end of the talk?
Oh, okay. What foundation?
Model encoder is used here.
Okay. For the foundation model encoder, it's mainly targeted for medical imaging tasks. So we usually use the convolutional layer for each layer. We don't consider the transformer here. Yeah.
So it is not transformer based. That's the
yeah.
answer?
Yes.
Okay.
Yeah.
I did not fully follow. So what's the foundation model you used here?
Oh, you mean foundation model? It's
You
up
have
to the
used
which. Oh, I know your meaning. It's up to the your tasks for segmentation. Foundation models. We use the set. We will talk about the details in the experimental part. But for the classification foundation model, we use the ResNet.
pre-trained.
Was it pre-trained, Jiangchao?
Yes. Yes.
What data? With what
Okay.
data?
What was it pre-trained on?
You mean the pre-training data? You mean the
Yes.
pre-training data? Yeah. Okay.
Yes.
That's a good question, but I will talk the detail in the experimental part. I will show the data and the foundation model types. Right.
Okay. Thank you.
Okay. So for the balancing among tasks, we can set different ranks for different LoRa's actually, according to the difficulty of the tasks. An empirical way to evaluate the difficulty of each task is by a warming up phase. Namely, we can use the backbone to train for a few steps, and then we can compute the loss statistics of each group. we can determine the difficulties of each anatomy based on the degree of the loss reduction in the warming up phase. Then we can follow this evidence to adaptively adjust the LoRa rank of each anatomy. The overall pipeline is summarized in this algorithm. And the training objective varies based on the task of medical foundation models. If it's for classification task, we can adopt the classification loss with distillation. But if it's for the segmentation, we can adopt the pixel-wise loss, including the class loss or dice loss, and then appending with the pixel level distillation. So basically, it's a general framework. We project the medical foundation model into another or collection of a mixture of experts to approximate the ability of original medical foundation models. So let me talk about the experiments. So this is the datasets we used for pre-training and downstream verification. And here, for the segmentation foundation, we use the SAT foundation models, SAT. In next slides, there's a reference about the medical foundation models. Okay, let me explain more in these slides. We mainly verify the performance of different methods in both the pre-training dataset and the downstream task dataset. The reason that why we need to evaluate the performance in the pre-training dataset because we try to use a collection of expert model to approximate the ability of the original medical foundation models. So we need to make sure that the fitting ability is also similar in the pre-training data. Then we verify the generalization performance in the downstream tasks. So for the segmentation foundation, I think Jianming asked my questions. For segmentation foundation, I use the SAT foundation models. At that time, the SAT foundation model is pre-trained by another team of our group. At that time, the performance of SAT is better than MedSam. And the competitive performance over the individual specialist unit. So we adopt this foundation models for segmentation task. As shown in this table, we can find the LoRKD performed on the segmentation foundation two versions, SAT Nano and SAT Pro. We can find that LoRKD performed better than its teacher model, the two versions, and simultaneously better than the NAUnet, which is the strong baseline on individual tasks. At the same time, we can also find that our model improved version requires only 25% parameters of the teacher model. Yes, that's the key. Yeah, the student can outperform the teacher. So let me clarify the reason. I think for the original pre-training task, if the data is more heterogeneous, we actually required very large foundation models to incorporate the discrepancy among the tasks. So if you don't have special design to consider this heterogeneity, so you have to large scale the model, very large scale. But given a special scale in the foundation models, we can use the such decomposed model architecture, like we use a common backbone to incorporate the homogeneous features or homogeneous patterns, and then we project the features into the task-specific LoRAs. Then we can mediate the conflict among tasks. So I think it's the reason that why students can outperform the teacher models. Another reason I think it's because it comes from the benefits of distillation. Conventionally, if we perform distillation, the student model can achieve better performance than the teacher model if we don't reduce the model size of the student model, right? Oh, okay.
May I ask a question?
Okay. I'm reading your question. The target task must be known in advance. Yes. That's the key. If we want to decompose the medical foundation models, we need to access the original pre-training data. So I think it's also the limitation, because if we want to, sometimes we cannot access the original data to pre-training the foundation models, then we cannot run on LoRKD.
Jiangchao, I think the question is the task known?
Okay.
Yeah,
Let
the data
me
set, but
check.
is
Yes, I see the.
During the pre-training phase, you know the target task, or you don't know the target task?
What a target task you mean? You mean the pre-training data?
no, as in the
Or
segmentation of
downstream
a
task?
certain. I think it's about the downstream task.
Yeah.
No.
Downstream.
No. Here the target. We don't need to know the target task.
Okay,
Here,
well, you don't need to know
what
that.
we show in this table is the pre-training data, pre-training tasks. And in the next slide, we will show its generalization performance to fine-tune the lightweight expert model in the downstream scenario.
Okay, thank you. I think another question is that your student and teacher models, do they have different backbones?
Yeah, different backbones. We actually use smaller encoder backbone compared with the original foundation model encoder. So that's why after the training we can get all lightweight expert model. No, because they have different backbones. So
so you're not initializing. Okay, so you're not initializing the student.
Yes, we just learn from scratch, and don't initialize the weights with the teacher model.
Okay.
In table 2, the highest score is for the original table 2.
Yes, I think it's the same table.
No, if you check the value, you can find the LoRKD star achieves the best performance.
Yes,
right?
I think you should be, I think, focusing on the average dice.
ASD, if you check the ASD metric, LoRKD Pro achieves 82. Right.
Okay, I think he got it.
Yeah.
And I think one other question is, what would be your perspective on having a single LoRa head for each of the downstream tasks?
Okay. As I so I use a single LoRa for each task.
Okay.
I use a single LoRa for each task.
Okay. Thank you. Let's move on.
Fuzzy or probabilistic MOE-like approach instead of single LoRa per task better. Maybe, but it also brings the concern that the training cost because let me clarify here. Although we can use a mixture, use a multiple expert model to approximate the or vanilla foundation models, the key problem is also about the training. The computational is also the problem because for a mini batch of samples, it may contains of different anatomies. Given saying that one sample corresponds to the head and one sample corresponds to your chest, and then we need to merge two LoRa into the backbone and get two models. Then the in this case in your GPU cache you will load two models, right? So the cache size is very large. Another the efficient way is transformate this computation into all group convolution. So as I explained in this slides. Okay. Which segmentation head is used in segmentation downstream? Okay. No, I still haven't reached to the downstream task. So in this table, I just want to say for pre-training data set, we use a mixture of expert models can approximate the ability of the medical foundation models. And at the same time, we can reduce the model size and achieve the better specialization. So this is the goal of this table. But for the segmentation downstream, I directly use the decomposed expert model to replace the foundation model in specific tasks for fine tuning. And then table 3 shows the performance compared with NUNet and the set nano and the set pro on the downstream task performance. And we also verify the LoRKD, the expert model fine tuning on the downstream task. You can see an interesting point is the specialized expert model can achieve fast and better performance in the downstream task. The performance gain. Sorry for Jianming's problem. The question: can you show the performance gain? Which performance gain? You mean the downstream task performance gain? So yes. In this table, this table, you can show the
what's your
LoRKD
foundation model's performance? Which was your foundation model?
Set nano and set pro.
So this is your
yes
model. So you want to learn from them. So this is your gain. That's right. This is your final gain. So this is your foundation model. That's right.
Yes.
So this one is, so which one corresponds to this one? This corresponds to this guy?
Okay. Let me use the, hold on. I want to compare LoRKD Pro into this one. This is the Pro set foundation model, and you can use the LoRKD Nano to compare the set nano foundation models.
I got it.
Yeah.
So this is 96.5.
So from the
62. So this is significant. Is this significant?
No. We can consider the average performance.
Oh, average performance.
Yes.
So you only have one run. That's right?
Yeah.
You have one run. So you will run multiple times. What's your standard deviation?
Okay. That's good questions. Actually, this is the experimental result of multiple runs, but we don't report the deviation.
Okay. I would like to see you have standard deviation and also the p-value to show you really have performance gain. It's significant.
Okay. We will add the result in the updated version. Okay. Actually, for this task, we want to say that the smaller expert model can approximate you can use the share of expert model to approximate the ability of or large medical foundation models, even in the pre-training data and the downstream generalization. I think the reason is also straightforward, because for medical foundation models, if the data is too heterogeneous, so you incorporate too much conflict during the training. I don't think you can learn better only because of you have a larger model size. Because we can also scale up the model size of the expert model, right? We can also scale up the model size, but compared with the medical foundation models, we actually reduce the model size. Okay. For classification, we use the ResNet. ResNet, I remember it's ResNet 124. If I'm right, I don't remember the exact the number, but it's the 100 layered, more than 100 layer ResNet, and in the classification pre-training, we pre-trained the data in the radio ImageNet and MedMNIST and the MedMT. Okay, sorry. Okay, sorry.
Jiangchao, I think you're gonna have to share again your screen.
Okay.
Yes,
okay.
please. Thank you.
Okay. So we can see the performance is more significant than that in decomposing medical segmentation foundation models. And the parameter size of our thin model is smaller than that in the teacher model. So do the foundation model always perform specialist? No. As far as I know, in some cases, the foundation models, especially the medical imaging foundation models, they cannot outperform the specialist always.
Then why you want to use the foundation model as your starting point?
Yes. Just use the foundation model as a starting point for fine tuning, and then possibly you can outperform the single age training in the downstream scenario. But if we can decompose,
this is all single trend. This is all singly trained, single task learning.
Yeah, single task learning and multitask learning and KD and KF. We compared more baselines in this task. So we can see for foundation models, it cannot achieve better performance even than single task learning and multitask learning. So I think the reason is because of the data heterogeneity. So you can scale up data, but at the same time, you need to scale up the model size. So there are some correlations between the model size and the data size.
So this is your model.
Yes.
derived
Yes.
from this foundation model. That's right?
Yes. I directly distillate the foundation models I use LoRKD directly distillate the foundation models
What
on the
about you
pre-training
use the
data.
knowledge from each individual ones?
Sorry.
What about you use the knowledge from each individual ones? Single task learning for particular task. Do it again.
Yeah. Compared with the multitask learning, I think it's not very significant. Yeah. What I want to say is because you can also notice the model size, right? Yeah, this is the model size.
Yeah, I know. I know your model size is smaller, and I mainly care about the performance.
Okay. I know your meaning. Yeah, I think you're right. Maybe if we I don't have more experience. Maybe I need to add more experience to support our experimental result by scaling up the student model size. Yeah.
Thank you.
Okay. So this is the classification pre-training, and for the downstream tasks, we in this table we also show it can be seen for the generalization performance. No, can we say that it's significant, right? Right? No matter compared with the foundation models or compared with the other baseline methods, right? But for this task, it's not. But for the red image net and MedMist, I think we can say that the performance is better. Okay. Here we also have a more comprehensive comparison between the vanilla foundation models and the decomposed expert models on segmentation and classification tasks. In terms of all the model parameters and flops during training and the serving phase. From this figure, we can say that except the parameter size and the performance, actually we can significantly reduce the number of model parameters and the computation flops. And for each task, we also conduct some verification to scale up the rank of each LoRa. In this table, we scale up the LoRa of each task, the rank of LoRa in each task, and as can be seen, the performance scale with R until R reaches all sufficient size. But when it reaches to all sufficient size, further scaling up R get no gains. So I think this enlighten us for some cases you don't need to fine tune the rank of R. You can set up a relatively larger rank for each LoRa, and then just let the model to allocate the model space during the pre-training, during the distillation. So, and in the bottom, okay.
I think we have a question from the audience. 2D and 3D data, can they be both handled at the same time, or do you need like different backbones for that?
Sorry.
2D and 3D data. Can they be?
Oh, I
Can they
see,
both
I
be
see, I
handled?
see. Oh, I see. The input can be CT, MI, X-ray. It depends on the medical foundation models. For the segmentation foundation models, it can be input the CT. For the for the classification foundation models, we just input the X-ray. So
Okay.
it's not up to our model. It's up to the medical foundation model.
Okay.
We
Okay. So
decompose.
it is basically dependent on the type and the modality. It's all dependent on the medical foundation model backbone that you're using. Thank you.
Yes. So in the bottom, we also visualize some examples to show that for the segmentation, for the classification, we can use the CAM to visualize the location accuracy of the lesions. And for the segmentation, we can directly compare the ground truth with the segmentation output. As it can be seen, that all LoRKD can be narrowed down the focus of the lesions compared with the foundation models in the segmentation, in the classification task. And in the segmentation task, LoRKD learns better for special segmentations on special regions. Okay. So that's all. Yeah. Thank you.
Thank you.
The questions, it's very inspiring for me, and yeah.
Thank you very much, Jiangchao, for very interesting talk. Before we move on to questions, I'd like the audience to give our speaker a virtual round of applause.
Okay.
And then I think I'm going to just go through the chat and see if there are any remaining questions. I think you got through almost all of them. Yeah, so if anybody has any more questions, please feel free to ask now. If not, then I can start with a small question. Jiangchao, very interesting. Do you see this idea kind of expanding into the multimodal domain? The whole vision language models, do you think like the same ideas could be used over there?
Yes. Actually, I want to clarify the limitation of this method. Currently, we only achieve the success in the vision domain. We don't achieve success in the language domain. I think it's because of the data heterogeneity. I think in the language domain, the language. We can simply use the heterogeneity to evaluate the language, because languages also have the common patterns in the taxonomy and some expression way and other ways. So I think in the language domain, especially medical language domains, the data heterogeneity may be not all big issue, but for medical imaging domain, the data heterogeneity matters. So I think I think maybe for language domain, our method is still far away from the success.
Okay. Kind of makes sense. So does anybody have any more questions? If not, then we can just give our speaker another round of applause and we can sign off for today. Thank you very much, Jiangchao. It was very interesting.
Thank you, everyone.
Thank you.
Okay. Bye.
Bye.